I'm an ecologist. I work in an organization called EcoHealth Alliance. We work in wildlife conservation and human health and do a lot of research into the wildlife origins of human diseases and how the interactions between humans and animals can be improved both to protect animals and reduce the risk of new disease spillovers. And that ranges from field veterinary work to app development work, data science in between, everything, wildlife to whiteboards. And involves a lot of collaboration and a lot of data sharing with many different groups having different skill sets, working in different paradigms around the world. I also, as Jared said, work with this organization, ROpenSci, that builds tools to help people, primarily using R, do more open and reproducible science. So we're really interested in making sure that the research that people do gets out into the world in a way that people can reuse the analyses and the data that originate in the lab and can go out into other research groups, into businesses, and so you can sort of have that multiplicative effect of that research do. And so in both of these contexts, I'm really interested in how data gets out. And when you talk to people who are in scientific reproducibility, who are librarians, there's sort of a series of best practices one has when you're sharing scientific data that people want people to adhere to. You want to make sure that data is in machine and human readable formats, so it can be future-proof. Your CSVs and TSVs, your XMLs and JSONs, all those formats, they can be parsed by lots of different languages. They probably will be able to be parsed by future languages. If people don't know that, you can open it up and inspect it and see what the problems are. That's thought of best practice. And you want to put those in long-term scientific library archives that have a lifespan beyond the current grant cycle, the current business model, people who have figured out how to do this sort of library-level archiving to make sure that we can have things available after your project wraps up. You want standardized metadata, so data can talk to each other, so they can link to each other, so people can use that information to understand what is in the data set they're looking at. And you need documentation of all of that. Now, one of the things we do a lot in the R community is package data into R packages, right? And it's kind of funny, when you put data into an R package, that doesn't necessarily work with this paradigm. Usually the data is in the RDS and RDA formats, which are binary and not inspectable and specific to a language, and even the R manual tells you it could change from version to version, so it may not be future-proof. GitHub and CRAN, which is where we put these packages, are great, but they're not necessarily built for long-term archiving at the scale that libraries and scientific repositories are. And when it comes to metadata and documentation, that's possible, but you may or may not do that because it's not enforced in the places that packages are put. Nonetheless, it is something we do a lot. So this is from a little project we did at the ROpenSci conference last year, where we were looking at how people use R packages to transfer data. And the first thing that pops out is that we do it a great deal. Almost half of the packages on CRAN distribute a data set in some way. Now, a lot of the times that data set is an example data set for a statistical method or for a function that is packaged in the library, but lots of those data sets are, here's an R package associated with a book, or an R package associated with a scientific paper, or something else where people want that data to get into the hands of people. But it doesn't meet those requirements. So why do we do it? Well, there's a bunch of advantages of having a data in the package. And the first is you get to hijack the package distribution and storage infrastructure. CRAN and GitHub, the places we host package, are very central, very visible, a lot less fragmented than actually the scientific data repository world. And so you have a lot of visibility by putting something up there. Secondarily, you have a local infrastructure for your packages on your computer. There's a package library, which can act as a data library, which means you can have a place where you have a single copy of the data that is shareable across projects. You're not going to fragment and have different versions of the data across your machine if it's available in a package. So that's great. You get to take advantage of the binary formats. They exist there for a reason. They're fast to load, they're fast to save, they can handle lots of different types of data structures, and so that's one reason to do it. And then when you build a package around data, you can facilitate the anticipated workflows around that data. You have data you're serving, you have assumptions and ideas of how people are going to use it, and you can facilitate those things by building functions in to have certain types of graphing of that data, certain types of processing of that data to help people along. And the linking of that software and data makes that analysis process easier if you can anticipate what the analysis process is. And then you can use the documentation system, which is built right into your analysis environment, your R console, your RStudio server. So you can document that data right next to where you're working with that data, and people can use it. So you have all of these advantages, but there are a bunch of different ways you can package data in R into an R package that vary in the degree of their trade-offs with these best practices for scientific archival and for different types of workflows. And so I'm going to talk about 3 and then kind of advocate for 1. So first we have data in packages themselves, which is what I've been talking about so far. Generally, this is going to be small data. If you're distributing through CRAN, CRAN has a 5 megabyte limit on the packages themselves, which means your data are going to be even smaller than that. It's generally going to be fixed. These systems are not designed for rapid iteration of the packages on those platforms. And so you're not really going to be having data that changes on a really regular basis packaged up. It's usually going to be at the end of a study, you put it there, you send it up. And that limitation is imposed by the hosting services, by these community groups that are managing CRAN or another package distribution like Bioconductor, like our own at ROpenSci. And for that reason, the data sets really are limited. So they're good for teaching data sets, they're good for demonstrations for your packages, but there's a lot that you can't distribute through the normal wrap the data in the package directly. Next, you have data API wrappers, and this is becoming a very common pattern for people to use across all sorts of disciplines and all sorts of businesses. Rather than putting your data in a package, you put your data online on a server that can serve it via a web API, and then one builds a package around those APIs in order to pull them down, and so people can query that API directly, pull some subset of that data or some query of that data, and it has some great advantages. The size can be unlimited. It's only limited by the server infrastructure that's out there, which means you could have server structures that involve many machines across many databases in many places. You can have live changes. Those servers are tied to other events, other web services. Things are changing minute to minute. You can make that query. It'll differ minute to minute. You're only limited by your server capacity, your systems, and what types of queries you can send and what's built into the API endpoints that you design. So that works well for this sort of targeted querying, for asking a question of a big data set where you can send that question up. But it's not as good for analyzing data en masse because you have to move that data every time you make a call. And for a lot of analyses, maybe the query doesn't have the ability to do that at the server level, or you have big computational demands. And if you're just trying to distribute these data sets to a lot of people, you may not be able to manage a server and have that infrastructure for them that's computational. Nonetheless, we build a lot of data API wrappers at ROpenSci. Biological, ecological, geological, chemical, all sorts of scientific databases exist out there in common data repositories. And we make a project of connecting them with these via R packages that wrap these APIs. You can grab lots of things. We work in labor and economic data, government social data. It's a whole spectrum. And this is just like a small screenshot of a very long web page that we have. And this is sort of our bread and butter. Nonetheless, I think what a pattern that we're using more and that I like more and more is the idea of data sync, where we have a limitation of local hard disk size, which is often adequate for a lot of the things that we want to do. So there are data sets which we serve in a static fashion on a remote source. And the role of the R package is to sync that remote source to your own computer and update it on some kind of regular basis. So you're not working with live data minute-to-minute changes, but you can deal with version changes across data sets as you have regular releases on a weekly or monthly or annual basis. And that's really limited by your local analyst resources, what can fit on a hard disk. But as long as you have that, you can analyze all of that data at once. And when you're doing sort of big global level analyses, which is a lot of what we do, that's the limiting factor. And we want to be able to capture all of the data together. So I really like this pattern. It's in the like megabyte to multi-gigabyte data scale. Now that doesn't work for everything. If you have click data ends up into terabytes and petabytes and who knows. But in my case, if a data point is not a click, but a person in a Tyvek suit in a forest all night catching a bat and swabbing its anus with a Q-tip, and that gets us one data point. When we get to megabytes and gigabytes, we're really doing well. It works well for this regular, but not live updates, and so we can have version data, which means here's an analysis at version 1 and not version 2. We have the speed and versatility of having the data locally when we work on it, and we can facilitate by wrapping this process in a package that has functions and documents for working for specific kinds of data. So how does a package like this work, and what tools do you use to build it? Well, the core that we've been using recently is a package called Datastore by a guy named Rich Fitz-John, who's also part of the ROpenSci Developers Collective. And Datastore is designed to manage this data sync process between remote and local sources and dealing with versioning. So the thing you get with Datastore is the creation of a data library. In addition to having a package library, you have a data library. And the rraptors and store packages are what enable us to do that and have it work agnostically across different operating systems, and keep things efficiently stored, so we keep the versions that we need and not the versions that we don't. It's able to deal with essentially any file type because you provide it with the load functions you want for your data. When you're building a package, it'll auto-generate the code for the core functions you need in order to use this package, which is great. Its default setting is to use GitHub releases as our versioning mechanism. So you attach data to GitHub releases, which let you attach data files of up to 2 gigabyte size per version. But there's a potential for other backends in the package. So we're working on making it connect with scientific repositories like Zenodo or Figshare or the Open Science framework, which also enable the sort of storage of large versioned objects. The other thing we really like to use is taking advantage of good file types in order to speed up the iterative data process. So you can use the sort of optimal archival CSVs and JSONs and XMLs, but often, because we have this sync and load process when people are working with the data, we want to make sure the data transfer is fast and the loading process is fast. So we want fast load formats and good compression. I really like FST for tabular data. There's a lot of good options out there for fast on-disk tabular data in R at this point between Feathers and FF and all of these things. FST is a great one. It works really well in taking advantage of local multi-threading. And the thing that I like a lot is it gets great compression without a lot of loss of load or write times. And so you're able to load multi-million row data frames in a matter of seconds. It performs at least as well as most of the options out there. And one of the nice things is you can store data and work with it on disk without loading to memory. There's an experimental package by, I'm going to get his name wrong, Carol Muller, to use a dplyr pipeline with these files. So you have the dplyr backend, just like it works with an SQL database. It can work with FST files. So an example of this, so we built a package for CITES. CITES is the Convention on International Trade of Endangered Species. We use this data a great deal to understand the flow of wildlife across the world. The organization has more than 40 years of data of essentially every wildlife trade between treaty countries that has occurred. But they didn't have a bulk way to export it. We needed to use it in bulk. So we built a package that uses these. And we've just put up a first version of it. So we have our version 1 of the data. But it'll update as we have new submissions to CITES. It updates on the order of months when countries submit their trade data. So it's not a minute-to-minute thing. But it's versioned. And that's important for us. And essentially how it works is you just have a function to call the data, which is CITES data. If it's not currently available in your library, it'll download that highly compressed binary off of the repository, in this case GitHub, and you can specify the version you want to load. So that'll load up. It moves relatively fast. But once you have done that a first time, 1.0 is cached on your computer. And so when you call it again, it'll load up immediately. And so we have quick access to, in this case, 2 million rows of data that is easy to work with across projects. Anyone can just add this function in, and you don't have to have fragmentation of the data sets across different things you're working with. Sometimes you don't have control of the upstream component of your data. So what we often do is have a data design pattern where we have pull from an API but sync to a local database that we maintain. So there's an SQLite database in our data library, and for different packages that, in this case, work with taxonomic data or infectious disease surveillance data, we sync that data down into the local database. You can work on it, and you just run sort of a single let's download the current database function. It'll pull it down, sync what you have locally, and you can work with it then. With the taxonomic database, we actually built originally an API package to do the calls, but because of the slowness of that access, we moved to this design. And so we actually have two packages. They have the exact same code API. So if in this case we're making a call, in this case we're doing a taxonomic lookup at the NCBI database, you can run it with an API call. It'll take a couple of seconds to pull down the data, making an HTTP request. Or you can do it with the version of the package that maintains a local database. And what we pull up is 10 times faster and actually scales much better to many requests, because you can vectorize the requests locally, but not to the API. Other sort of helpers we use in packages like this is giving a package status. So when you load up your package, we show the status of the local databases, which tables you have available, what you've downloaded, when you've downloaded, what you can update. And so this is helpful. It's especially helpful for our case where the table availability depends on one's security permissions across the shared project. So maybe you'll have some data and not others. It shows what's available when you load it up, which is helpful for an analyst. One of the other patterns we've been using across these data access packages is in making metadata useful. So a lot of times when there's a big data set available in a public repository, there'll be a code book or a metadata sheet along with it that has something like the descriptions of the codes that are there, the units that are available for the columns, the descriptions necessarily of what came. And it's often in a document like this, a PDF or a doc. And it's there for good reason, because they expect people to read it with their eyes. They want people to be able to scan it and look something up. But then you don't have the ability to work with it in a computational way, for instance, to link codes and descriptions for visualizations. So for the case of CITES and some other projects that we've worked on in this case, we use a package called Tabulizer that wraps the Tabula PDF library, which can extract that data into a structured tidy data frame. And so every time we download this PDF data, it becomes tidy data. So you can work with that data. But then there's the reverse problem. This tidy data, this data frame, contains a lot of values, and you want to be able to scan it quickly, to search it, to use it for lookup purposes. And so we had this approach where while we have the data itself available within a package, we also build it into the help files as an HTML widget. So if you search for help about the metadata of a package, it will pop up an HTML help file which has a searchable data table. A lot of people don't realize that our help system is capable of very rich HTML markup. You can have images, you can have forms, you can have all sorts of things you would have on a web page. It takes some Rube Goldberg, because you've got HTML and JavaScript inside our documentation files, inside our Oxygen comments, and there's a lot of escaping and fixing you have to do. But we implemented in CITES. I'm hoping to wrap it into sort of a helper package for this purpose too. And then finally, we provide analysts with breadcrumbs. So one of the things we implement across things is print functions that flag conditions in the data that might be important. For instance, if there are field notes associated with the fields and the subset you pull up, we show those flags so that people know, look at the notes, or it might show there are duplicate fields in this data. And so that helps people as they're exploring data, but since it's only involved in the interactive print methods, when you actually implement a data pipeline, you don't have the performance hit of doing those lookups and checks every time you print, but it helps people understand the data as they get it. So in sum, if we're designing data packages, we have choices. We can store the data, we can query the data, or we can sync the data. And that choice really depends on your data scale and your time rate of your turnover. I think syncing version data is something that is very useful and is useful at the scale of data that a lot of people work at. It's helped with these efficient formats like your feathers and your FSTs and moving an SQLite database back and forth. And then when you do that, you can build rich documentation and you can build guideposts for your analysts along the way. And all of these things help us sort of minimize the trade-offs we have with sort of archival storage problems. And I think as we develop a few more of these tools, we'll be able to connect with the scientific backends with all of the efficiencies that we get with these API and syncing approaches. So that's it. Thank you very much.
Thank you.